My interesting mathematics project is about fractals. So a fractal is any of various irregular curves or shapes for which any suitably chosen part is similar in shape to a given larger part when magnified. Another example for fractals are roots. So for example, we've got a tree here. This tree is 80 years old. Now take a look at its root system. That looks pretty developed. So if you focus in here on this boxed out portion, the magnified portion, you can see that it looks very similar to the whole thing. The pattern of roots here looks exactly the same as the entire root system, theoretically, because it is a fractal. Now in nature, it doesn't continue infinitely, so it's not going to look exactly the same, but in theory it does. Although fractals were originally introduced in 1918, the person who coined the name as well as brought purpose to this concept of math was Benoit Mandelbrot. He pointed out the many uses for fractals from modeling many natural phenomena to even the behavior of the stock market. Mandelbrot created the computer-generated Mandelbrot set in 1980 using a very simple equation. Euclidean geometry is a form of math with perfect figures such as circles, triangles, squares, and cubes. However, these don't exist in nature. Fractals represent the imperfect figures that exist in nature, such as trees, blood vessels, lungs, snowflakes, lightning, and mountain ranges. This is the equation for the Mandelbrot set. Z sub n plus 1 equals z sub n squared plus c, where c and z are complex numbers, n equals 0 or a natural number. First, start off with z equals 0. Put the starting location into C. Then take the result of the formula and put it in as Z and the original location as C. This is an iteration. I'll give an example now. Remember that the formula for the Mandelbrot set is z sub n plus 1 equals z sub n squared plus c. Let's suppose c is 0.5 plus 0.5i. This is in the complex plane. First, start off with z as 0. So 0 plus 0i, then square it and add c. Take the result of this formula, 0.5 plus 0.5i, and plug it in for z for the next equation. Continue this infinitely. This is why fractals are usually used in computers. This is a Sierpinski triangle, which is a fractal described in 1915 by Wacław Sierpinski. This is a pattern that is repeated for the smaller triangles and essentially has infinitely many possible iterations. So the sequence starts with one triangle. Each triangle in the sequence is formed from the previous one by removing the equilateral triangles formed by joining the midpoints of the edges of the previous triangle. If this process is continued infinitely, it produces a fractal called the Sierpinski triangle. The formula for the Sierpinski triangle is n equals 3 to the power k minus 1, where n is the number of triangles and k is the number of iterations, which are the repetition of a process. Again, even though it makes a very complex figure, it's a very simple equation. Drawing a fractal is a very easy process. First, draw a large version of a shape that you want to be repeated within itself. Then choose a rule that you'll repeat over and over. Apply this rule to your image or shape over and over and keep going until you can't draw the details. Or if you're using a computer, continue infinitely. This is the Von Crush snowflake, which was discovered in 1904. It has six-fold symmetry just like a natural snowflake. It consists of 3 identical parts, each of which in turn is made of 4 parts that are exact scaled-down versions of the whole. Fractals are beautiful designs that are present in our lives every day. Fractals have potential even in medicine. Computers can be programmed to recognize the correct pattern of fractals in the pulmonary and circulatory system. This information can be used to tell when the body is diseased. Fractals have also been present in architecture throughout many cultures. Fractals have been present in our lives all throughout history,
and who knows how humans will use them in the future.